Okay, hello everyone. We're going to be going over the convolution integral, how to do it graphically. And so here it's going to be, if we remember with convolution, what must occur is basically we have our yt, so that's our output, is equal to the integral, so it's from negative infinity to infinity. And then it's the weighted sum, so x tau, and it's h of t minus tau, d tau. And so what we can say here is it's going to be equal to x of t convoluted with h of t. And so the convolution operator is given by this multiplication star. And so what we need to do is, if we have, for an example, x of t is equal to u of t. Then we have h of t, which is the unit impulse response, is equal to 3/2 e to the negative t u of t. Find y of t equals x of t convoluted with h of t graphically. So if we were to do this graphically, what we need to do is, first things first, we're going to have to convert this to the convolution integral form. So our x of t needs to get put in terms of x of tau. And so let's look at that. So if we're going to do the unit impulse response with tau, and so this is going to be x of tau, what that is going to look like is, it's the unit impulse response, so it's going to look like this. And then at time 0, it goes to 1. And then we're going to have h of tau. And so our h of tau, let's draw that. H of tau, and then here on the x-axis, this is tau. It's going to be 3/2. So that goes up here to 3/2 times e to the negative t ut. So goes like this. It doesn't occur till time 0. So this is our h of tau here. And so what we need to do is then we flip it, because we do h of negative tau. So what this graph looks like is, after you flip it, it's going to look like this. So it's going to be like something like that. And that's going to be your h of negative tau. H of negative tau here. And then you're going to have jump. And so you have to shift it over. So if we were to shift this, I'm just going to show you guys what that's going to look like so you know ahead of time. So you know what h of t minus tau is. H of t minus tau. That's going to basically mean for at any point t, that's how I think of it, you jump it over. So you move it over, so that's going to be so you just shift it over, so shift to the right, and then if you have a negative t, it shifts it to the left. But how I think of it, sort of, is this is your flip here. So let me do it actually in a different color. So this is your flip and your jump whenever you see it. Because if you recall, you can write it in the other form. But basically what we do is we take our original, which we had our h of t, so we just replace it with h of tau. We flipped it across the y-axis, and then we jump it with t. And so that's how we got h of t minus tau. So now going back to the integral, we got x of tau, and we got h of t minus tau. And now we're going to have to do the two multiplied by one another, because they're multiplied by each other in this equation. So let's just show it specifically at each interval, okay? And so let's just go at time t equals 0, okay? Because I want to keep this as straight as possible. We're just going to look at time t equals 0. So at time t equals 0, what it's going to look like is we're going to have our h of 0 minus tau, and then we're going to have our x of tau. And now that we got that, that's at time 0. And so what this integral is looking for, I want you guys to keep in mind, is that this integral is looking for the area under the curve. And so is there any shared area under this curve? And there's not, because the graphs do not overlap at all. So overlap equals 0. And so there's no shared area. So the convolution integral at time t equals 0 is equal to 0. Okay, let's now just move it over a little bit. So I'm just going to shift over to time equals about, I'm just going to say 0.5 seconds. And I'm just sort of eyeballing what it's going to look like, so you guys know. But if we shift it over a bit, this h of t minus tau is now going to be h of 0.5 minus tau. And then the x of tau, it just stays in place for this entire thing because it's in terms of tau. It's not in terms of t. The only term that's in terms of t is the h of t minus tau. So this would be h of 0.5 minus tau, whereas this is going to be still our x of tau. And now the area that overlaps between the two is going to be this right here. So that's the area that is shared between the two. So the overlap, the area under the curve, overlap is going to be greater than 0, specifically. And so here we have overlap greater than 0. Then let's look at time t equals 1. So I'm going to get another sheet and just show it right here. At time t equals 1, we're going to have the two curves and so what's going to happen is then we shift it over a little bit more. So and we're going to see that the UT, so this is our x of tau, and the other one is going to be our h of 1 minus tau. And so the two now, the overlap is going to be at its peak, right? Because that's when the most amount of overlap is occurring. So the overlap is at its peak because that's the most amount. And so what we're going to see then at time greater than, any time greater than, basically, I'm just going to choose an arbitrary point, t equals 3. we're going to see that the overlap is exactly the same. And so what's going to happen is the overlap is going to remain exactly the same as we see with our excital. And so here, excital. And then this would be now shifted over about 3. So the overlap is exactly the same under the curve here. Exactly the same. And so since it's the same, when we do t equals 1 and 2, t equals infinity, since the unit step goes on and on and on forever, what we're going to see is that this graph, or specifically y of t, which is a graph of the overlap, which is equal to the negative infinity over infinity between the two curves. If we now look at it, what's going to happen is the area under the curve. Look at now all of them at once. Well, I'll try my best to. But in the beginning, at time t equals 0, there was no overlap, right? And so here, going back to the curve down here, I'm going to say at time before 0, there was no overlap, so it's 0. Then when time greater than 0, we shifted this one more to the right, this pink curve, which is the h-ital. So we started shifting it to the right here, and there was some overlap. And so the overlap here, I'm going to show that on the curve. There was some overlap, so it was increasing as we kept moving it to the right. And as we kept moving this pink one to the right, it got larger. And then it reached its max value, because that max value, it's going to stay the same as it shifts to the right since it's the unit impulse. And so the area is going to remain constant. So that's where the area under the two curves remains constant. So that's why I can have a constant curve here. So this represents my y of t with time. And it just shows that the area of overlap, in the beginning, there was no overlap between the two. Then there started to be some overlap, and it reached its peak value, and then it stayed the same because of the unit step response. And if there wasn't a unit step response here, if it like turned off somewhere, then the area would go back down to 0 on the curve. But that is the explanation of convolution and how it works.